This episode of Real Engineering is brought to you by the Curiosity Stream and Nebula Bundle Deal. Sign up now to watch the hour-long version of this video linked in the description. Jet engines are a marvel of engineering. From precisely controlling the internal atomic structure of metals to create turbine blades that are actually one single crystal, to delicate robotic machining that humans could only have dreamed of a decade ago. The jet engines of today are barely recognizable to those of the 1940s. They're bigger, they're more powerful, and they're more efficient. The Dreamliner's engines are so big that they are the same diameter as the 737 fuselage. And this is just part of the puzzle that has allowed the 787 Dreamliner to break world records. In March 2020, in the midst of a global pandemic, the US government imposed travel restrictions on all European travelers. A move that cut off France from one of its far-flung territories in French Polynesia. Business as usual for Air Tahiti was no more. A creative solution had to be found to replace their regular flights between Tahiti International Airport and Charles de Gaulle Airport, which, under normal circumstances, stopped over in LAX. Faced with disruption, Air Tahiti began operating the world's longest flight, a 16.5-hour, 15,700 kilometer non-stop flight between Tahiti and Paris, the world's longest distance scheduled flight, and it was technically a domestic flight. The 787 made that possible, and today we are going to learn how. In our last video, we explored the incredible engineering that has gone into sculpting the airframe of the 787, but all of that work is useless without a power system to match. Boeing transformed the way airliners are powered to create a plane like no other. The first step in powering a large plane is to get the jet engine started, and that itself is a very power-hungry process. We need to get the compressor section turning in order to achieve adequate compression for engine ignition. We have all seen footage of people hand-cranking old piston-powered planes to get them started. This obviously is not feasible for jet engines, which need to rotate at very high speeds to start. Engineers have dreamed up many ways to complete this job. Some engines use explosive cartridges that look like shotgun shells that will be fired by an electric charge. The hot gas is expelled by the cartridge, then drive a smaller turbine, which is connected to the drive shaft through a reduction gear, allowing the smaller turbine to get the engines up to speed. Cartridge starters were popular in older military planes that may need to get into the air on very short notice with limited ground support. Some planes, like the SR-71, had a direct drive starting cart, which connected two massive V8 engines directly to the J58 engine from underneath the nacelle to get the powerful jet engines up to 4,500 RPM. However, air starting is by far the most common method, where pressurized air is fed into the turbine section directly to get the engine moving. This can be done with an external cart called a hover cart, which connects hoses to the engine. But most commercial airliners are capable of generating their own pressurized air with an APU, or Auxiliary Power Unit. These are smaller turbine engines located at the tail of the aircraft that are small enough to get started with a battery and an electric motor. Most people aren't even aware this mini turbine engine exists, but you can see the exhaust here on all modern commercial airliners. The 787's APU, like other planes, is started by a small battery, but from here, the 787 system architecture is very different. The 787's APU, like other planes, is started by a small battery, but from here, the 787 system architecture is very different. The 787's APU does not provide pressurized air to the engines. It provides electric current to two electric motors attached to each engine, which act like the starter motors on your car. However, these motors can act as generators to provide the 787 with unparalleled electric power. A traditional plane has one generator on each engine and one on the APU, but the 787 is anything but traditional. There are, in total, 6 generators on board, with 2 pairs on each engine, providing the main power. each capable of generating 250 kilowatts, with 2 more on the APU providing secondary power, each capable of providing 225 kilowatts. If all 6 of these generators were running at the same time, that would be 1.45 megawatts of power available to the 787, 4 times more than a 777 is capable of producing. To put that into perspective, this is a 787 on a football field. If we needed to generate that electricity with solar panels in the middle of the day, we would need to cover about 10 football fields with solar panels. This is a lot of power. So why did the 787 need that much power, and where is it all going? The 787 uses a no-bleed air architecture. Traditionally, many aircraft systems are powered by hot compressed air drawn from the compressor section of the jet engine. The APU normally provides hot air to the engines to get them started, and then, once the main engines are started, hot compressed air bled from the compressor section drives several important systems. Normally, air conditioning and cabin pressurization is handled by the bleed air system. The bleed air would be drawn from the engine at a temperature upwards of 230 degrees Celsius. This obviously would quickly turn the cabin into an oven, so the air would first run through a complicated air conditioning and pressurization system, where some of the air is cooled using a heat exchanger, which uses outside air from a surface-mounted intake called ram intakes to remove heat from the engine bleed air until it is a suitable temperature to be distributed through the cabin. So, we are doing work to remove energy from this valuable bleed air from the engine. This is obviously rather inefficient, and all that ducting is heavy. And this is why the 787 does not use this system. Its cabin pressurization is handled entirely electrically. We now have 2 inlets, the ram air inlet and the cabin air compressor inlet. The cabin air compressor leads to, you guessed it, the cabin air compressor, an electrically driven device that compresses the air for the passenger cabin. This compression process heats the air up too much for direct use into the cabin, so it does require some cooling using a heat exchanger cooled by the ram air inlet. You can see this little door open while the plane is on the ground, and it serves to protect the inlet from foreign objects entering it. Another energy-intensive process that has been handed over to the electric motors is the braking system. As you can imagine, the energy required to slow down a 200-ton plane traveling at 270 kilometers per hour is not small. Calculating the energy required is pretty trivial. We just need to calculate the kinetic energy of the object, which we can do with this equation, and that gives us a kinetic energy of 562 million joules. That's a lot of energy, and the vast majority of that energy needs to be dissipated by the brakes of the plane. Reverse thrusters can deploy that redirect air from the bypass ducts through slots that open on the side of the engine. So, the brakes need to convert a lot of kinetic energy into another form of energy, heat energy. You can really see this in effect during a plane's most extreme brake test, an aborted landing test. Here, the plane is flying at full load, including the weight of the fuel, and has to abort at its V1 speed, the absolute maximum speed a plane can abort a landing at. Beyond that point, the plane has to take off. When the plane comes to a full stop, the brakes are glowing red hot. Typically, the braking mechanisms of planes is driven by hydraulics, with a hydraulic piston forcing the brake pads against the wheel to slow down the plane. The 787 removed this bulky hydraulic system and traded it in for brakes actuated by electric motors. Each of the 8 landing gear wheels feature one of these units, and together they helped eliminate between 62 to 111 kilograms of weight from the 787, while also being drastically easier to maintain and install. The 787 does have a hydraulic system, however, but it has eliminated 2 large bleed air-driven hydraulic pumps that are normally used to meet peak demand during takeoff and landing, where landing gear actuation and deployment of high-lift devices like slats and flaps would overload the other pumps that power the hydraulic system during cruise. The 787 had the added electric power needed to rid itself of these bleed air-powered pumps and replace them with more efficient electrically driven pumps. To boot, the 787 is able to generate higher hydraulic pressures that allow it to use smaller hydraulic components, which saves both weight and space. So, that covers most of the system architecture, but we haven't even touched on the revolutionary engines themselves. The Dreamliner is most commonly fitted with two General Electric GEnX engines, each capable of producing between 310 kilonewtons and 360 kilonewtons of thrust, about the same thrust that General Electric's previous generation engines, the CF6 equipped to the 767, were capable of producing. But the GEnX produces this thrust while consuming 15% less fuel. That's an incredible leap in technology. The GEnX achieves this primarily through two major design features that were not possible with older engines. The first is a gigantic bypass duct that surrounds the main engine. The primary components of modern-day jet engines are the fan, a compressor, a combustor, a turbine, and a nozzle. The ultimate goal of a jet engine is to draw in air and pressurize it as much as possible, which increases the energy potential of the air before mixing it with fuel and igniting it, causing a rapid expansion and acceleration of air. The work done by the compressor is then recovered in the turbine section, which powers both the compressor and the fan. Finally, the air, with its remaining kinetic energy, travels through the nozzle, where it is accelerated more and sent out the back of the engine to provide thrust. The engine core, this part of the engine, is what powers the engine. Yet, most of the air that travels through the GEnX bypasses this section completely, only passing through the fan and through this bypass duct, and this is one of the reasons the engine is so incredibly efficient. Bypass ratios have continually increased over the years, which is one of the reasons engines keep getting bigger. The GEnX engine has a bypass ratio of 9:1, meaning for every kilogram of air that passes through the engine core, 9 kilograms flow through the bypass duct. This is extremely high. The engine the GEnX replaced only had a bypass of 5.7, which, during its time, was itself a very high bypass ratio. While the core takes a small volume of air and accelerates it rapidly, the fan takes a massive volume of air and accelerates it just a little, while not requiring it to be mixed with fuel and ignited. This drastically increases the fuel efficiency of the plane. The fan essentially acts like a gigantic propeller. The industry has been aiming for larger and larger bypass ratios for decades, but there are a couple of limiting factors that make it difficult to increase the size of the fan blades. The compressor and fan are driven by the same shaft, meaning they rotate at the same speed. But because the fan is so much larger than the compressor and turbine blades, the fan experiences much higher centrifugal forces, and if the fan blades grow too long, their tips could even break the speed of sound, leading to shockwaves and a massive increase in drag. The first problem we need to address is how to handle those centrifugal forces. The magnitude of the centrifugal force can be found using this equation, where m is the mass, w is the angular velocity, and r is the distance from the center of rotation. So, our force will increase with the weight of the blade, the speed of its rotation, and its diameter. We want to increase our diameter to increase our bypass ratio. So, we need to figure out ways to either decrease our weight or decrease our rotational speed. The GEnX achieved the first requirement by using lightweight carbon fiber fan blades. Older fan blades were constructed from titanium being used for its excellent strength-to-weight ratio. But carbon fiber blades have an even higher strength-to-weight ratio, while also being much stiffer than titanium, allowing the carbon fiber composite blades to be longer and thinner than their titanium counterparts. This form factor even allowed General Electric to reduce the blade count from 22 to 18. In all, this resulted in a 15% weight savings in the blades, allowing them to spin faster without worry of damage. However, Composites do have one huge drawback: their impact resistance. One of the tests engines need to pass to reach certification is the chicken gun test, which, as you may have guessed, involves yeeting a dead bird into the engine and seeing how it holds up. The fan blades are the first part of the engine any foreign object will encounter, and thus need to be capable of withstanding the impact. Early development of composite fan blades by NASA and GE showed that composite blades by themselves simply were not up to the task. To solve the issue, the leading edge of the blades are reinforced with titanium. Bypass ratios are likely to continue growing as our technologies develop. Speed reduction gears between the main drive shaft and the fan may allow engine manufacturers to increase bypass ratios even more. Pratt & Whitney employed this technology in their PW1000G engine to achieve the largest bypass ratio ever seen in a commercial airline turbofan engine. They included a planetary gear between the main drive shaft and the turbofan drive shaft, which applied a 3-to-1 reduction in speed, allowing the turbofan to spin at a lower 4,000 to 5,000 RPM. This enabled the fan to grow in diameter, as the forces the larger blades had to endure were drastically reduced with a lower speed, giving the engine a record-breaking 12.5-to-1 bypass ratio. General Electric considered the design for their new LEAP engine currently in use by the 737 MAX, but problems with weight and maintenance of the planetary gearbox deterred them, and that hesitance may have been justified, as the engines have had a turbulent operation history with several groundings and engine removals, although these issues were not directly a result of the planetary gears. However, as the technology improves, we may see more of these geared designs being used to drive even greater fuel savings. The next design feature that helps the GEnX to reduce fuel consumption is the extremely high compression ratio achieved through the engine's compressor section. Compression ratio is the ratio found by dividing the pressure at the exit of the compressor section by the pressure at the inlet. This one variable has huge implications for a plane's fuel efficiency, and just as we can see a clear upwards trend for bypass ratios over time, the same can be seen for pressure ratios. The reason for this is fairly simple. By increasing the pressure ratio, we can maximize the energy we can extract from our fuel, because there is more useful energy available for extraction in our turbine and nozzle than if we compress the air less. But it's not quite as easy as just increasing pressure across our compressor. In order to achieve higher compression, we may need to increase the number of compressor sections, which will increase the weight of the engine, which will increase fuel consumption and reduce the advantage. Higher compression will also lead to higher temperatures, which may cause material failure in the compressor blades. And perhaps most critically, increasing the temperature results in increased emissions of potent greenhouse gases like nitrogen oxides. Nitrogen oxide formation rates rise exponentially with flame temperature to break down nitrogen molecules in the air and allow them to combine with oxygen. To facilitate increased pressure ratios while hitting climate change goals, this problem had to be addressed, and they did it through ingenious fuel injection technology. The compressor feeds its high-pressure air into 22 fuel-mixing nozzles located in a ring around the compressor exit. Their job is fairly simple: mix the fuel into the air and ignite it. A simple job that started development in 1995 with both General Electric and NASA. The art of crafting the perfect fuel injection nozzle is incredibly complex, a delicate yet violent process, like an orchestra whose crescendo is a fiery explosion. With the advent of 3D printed manufacturing, GE has been able to create a fuel injector with a complex internal labyrinth of air channels that traditional tooling simply could not cut. The fuel injector they developed is called the Twin Annular Pre-Swirl Injector, or TAPS. So how does it avoid those dangerous nitrous oxide emissions? By carefully controlling the air-fuel mixture ratios to control flame temperatures. If we plot flame temperatures against air-fuel ratio, we get something that looks like this: the max flame temperatures occurring at stoichiometric air-fuel mixtures. That is, the mixture where air and fuel are both entirely consumed in the reaction. This is the zone where nitrous oxide emissions are highest because the flame temperature is highest. To minimize nitrous oxide emissions, we can aim to be over on this side of the curve with a rich air-fuel mixture. But that would result in a lot of wasted unburnt fuel. So instead, we aim to be over here on the lean side of the graph. If we map the combustion process for GE's previous injector fitted to over 22,000 CFM56 engines, we would see the air-fuel mixture is initially injected in this zone with a rich air-fuel mixture. Then it goes through a dilution process to reach a lean mixture where the fuel is fully consumed. The issue with this is that the fuel goes through the stoichiometric region in between these two phases, creating a great deal of nitrous oxides. The TAPS fuel injector looks like this, with a central main pilot surrounded by a ring-shaped main injector, creating two swirling airflows that look something like this, which uses a large amount of air in the pre-mixing phase to ensure thorough mixing and a lean air-fuel mixture. If we map the combustion process of TAPS, it starts in the lean zone and gets even leaner further into the combustor, never getting close to the peak nitrous oxide production region. This may seem like a simple device, but it took generations of design iterations with computer simulations gradually bringing the engineers closer to their target. And none of their designs would have been possible without current generation metallic 3D printing that could manufacture the complex parts with the materials capable of resisting the enormous heat within the combustor. 26 years of development paid off with 60% nitrous oxide emission reductions, a fuel injector compatible with the record-breaking 58:1 pressure ratio used in the GEnX. GE managed to increase the pressure ratio even though they reduced the number of compressor stages. Each of these turbine discs is one stage. The GEnX contains 10 stages, 4 fewer than the CF6 engine it is replacing. GE managed to do this through new improved blade design, which is a lot less info than I wanted to share, but finding information on this topic was incredibly difficult, a testament to how advanced and secretive the technology is. The compressor does include 3 blisk stages, which are perhaps the most impressive feats of machining I have ever seen. Traditionally, compressor stages are made by attaching the blades to a separate disc with dovetail connections. This decreases manufacturing complexity, but the dovetail connection is less durable, increases assembly and maintenance costs, and allows some air to escape through the connections. Blisks are compressor stages that are manufactured from a single piece of metal, making them stronger and easier to install, while improving aerodynamic efficiency. Improving aerodynamic efficiency was the name of the game to improve compression ratios. And of course, that needed to apply to the turbine section that powers the compressor. It too benefited from cutting-edge aerodynamic modeling. The turbine also made use of new material science breakthroughs, being the first commercial engine to make use of gamma titanium aluminide, an advanced alloy of titanium and aluminium that combines the heat resistance of titanium with aluminium's weight savings, replacing the nickel alloys of past. It took 3 decades to take this material from the lab to commercial use, and the Dreamliner was the first plane to make use of it, paving the way for the material's acceptance in the industry. All of these factors combined to allow the GEnX engines of the Dreamliner to reduce fuel consumption by 15% over previous generation engines. That is an astronomical leap, and on top of all that, the engine is 60% quieter than similar sized planes. In part, thanks to the engine's most distinctive feature, this sawtooth pattern on the fan casing and the engine exhaust. These features are called engine chevrons, and they aren't just futuristic cosmetic design, but functional parts of the engine that significantly reduce engine noise. The question is, what difference can a mere shape change at a nozzle exit have on the overall noise pollution produced by the aircraft? Because turbofan engines force air out of their bypass chambers and turbines at speeds that are much higher than the speed of the ambient air, the air interacts with the free stream air, causing mixing. This mixing causes uncontrolled vortices, which in turn generate excessive noise for both the passengers and the community on the ground. Think of it like water accelerating down a waterfall and striking the water below. That turbulence can be extremely loud. The chevrons aim to control the vortices that are shed from the engine nozzle by creating smaller vortices at each of the teeth of the chevron to allow the hot, fast air being expelled from the engine to mix with the ambient air more gently. This is said to reduce jet blast noise by as much as 30% and allowed Boeing to use substantially less sound insulation in the fuselage walls of the aircraft, which helped to reduce aircraft weight. The 787 truly does live up to its name. It provides a passenger experience that is almost incomparable to that of other commercial aircraft, with advances in noise reduction, fuel efficiency, and passenger comfort. This series is usually saved for aircraft and technology most of us will never set foot in. But the 787 could be the most advanced piece of engineering we have ever covered, and it's a plane many of us will have the opportunity to fly in and marvel at the decades of engineering advancements that made it possible. This nearly half-hour-long video is just half the story, but the full hour-long director's cut version has been available on Nebula for over a week. It combines the two halves of this video released on YouTube into one seamless, ad-free experience that you can sit back and relax to watch. I removed one section from this video detailing the complicated thermodynamics explanation of why compression ratios actually increase efficiency, because it felt just too academic for YouTube. But I think die-hard fans of this channel may enjoy listening to a 10-minute explanation of temperature entropy diagrams. The director's cut also includes explanations of the 787's nifty electronic heads-up display in the cockpit and electrochromic window shades. I felt neither of these topics really fit in anywhere in the larger script. Nebula is the best way to experience our videos. No ads, no distractions, and director's cuts of videos when possible, along with exclusive access to our World War II series, The Logistics of D-Day, and our upcoming Battle of Britain series. If you want to see more content like this, the best way to support the channel is by signing up to Nebula with the Curiosity Stream bundle. I've included a link to the director's cut in the description for those of you already subscribed to Nebula, or if you've yet to start supporting the channel there, you can sign up through the Nebula and Curiosity Stream bundle deal for just $14.79 a year. That's over $1 a month, but that $1 has a gigantic impact on this channel, because we get to own and run our own streaming platform, and that gives us the freedom to create what we want, how we want. A little over $1 a month. This is by far the best way to support this channel and get something in return, with access to both Nebula and all the amazing award-winning documentaries on Curiosity Stream, like this one called Hack the Moon, about the fascinating technologies engineers developed for the Apollo moon mission. You can sign up to this amazing deal by clicking on this button on screen right now, or if you are looking for something else to watch right now, you could watch our last video on how vapor cones form on planes, or you could watch Real Science's latest video on how bee communication is helping us learn about the human brain.